We'll be seeing the minimization of DFA technique today. The minimization of DFA for the given DFA, we are going to take three examples. One with a single final state, another one is going to be with a multiple final state, and last one is with a unreachable state. Let us see the definition of or steps of the minimization of DFA. So the next topic we are going to see about is the minimization of DFA. So we are going to minimize the DFA expression into a minimized DFA with the minimum states. So what you are going to do here is we will split the states into two sets. One is going to have a final states and another one is going to have non-final states. Now we are going to split this sets into individual sets based on their equivalences. So how do you find the equivalence? So if you have a two states from the same state, if they are allowed to stay in the same set, if their inputs are equivalent, okay? So if they are not equivalent, then these two states cannot stay in the same set. So they will be kept in a separate set. So we will see an example how it is done, then you will understand how this works. So I simply say that first you split the states into two states. One is final states and another one is a non-final states. So that will be your zero equivalence. So next equivalence, how do you do is, in a particular set, choose any two states and check their input. If they are equivalent, then they can stay in the same set. Otherwise, they have to be in a separate set. So similarly, we will be checking for each and every variable with the other sets. So in this way, you will try to minimize the DFA. So let us have an example. So now let us take the example. This is a DFA with a single state, final state, and A is your initial state. So this is the diagram. So first we will write the transition table. So state for the input 0 and for input 1. So for A, when it is 0, it goes to B, and when it is 1, it is going to C. Similarly, we have B. So on 0B, it goes to itself, then it goes to D. So similarly, we will do for other things. So C go have B and C. D will be having B and E. And finally, E will be with B and C. So from the diagram, we have formed the transition table here. So this is your transition table. So first step is calculate zero equivalence. So how do you form the zero equivalence set is? So you will form all the non-final states sets in one set and final sets in another set. So let us write the non-final states. So the non-final states are A, B, C and D, and the final state will be kept in a separate set. So now this is your first step. Now we will calculate the equivalence 1. So we are going to calculate the equivalence. So zero equivalence is done. Now we are going to calculate first equivalence. So first we will take two states from the zero equivalence. So let us assume if it is going to be A and B. Okay. So see the input for A and B. So BC and BD. It is for 0 and 1. So check all the inputs are in the same set. So B, C and D all are in same set. So A and B can still stay in same, A and B can stay in same set itself. Okay. So you will have A and B in same set. Now the next state is C. You can check either C with A or C with B. So you are going to check AC here first. So see the AC. So for B it is BC for 0, 1, and for C it is again BC. It is identical. So they can stay in same set. So you will have C also here. So if AC fails, then you can check with BC. Otherwise, it is not required. Now we will check with D. D can be checked with either A or B or C. So let me first check with D, with A. So AD, it is going to be BC and BE. Now you can see here E is not in the set, so D cannot be in the same set. So we will form another set for D. So this is your first equivalence. All the sets are done. Now the final state set is included. Now step 3 is to find second equivalence. So we will start with the first equivalence table. Now we will check these three are there, whether these three can exist for two equivalences or not. So we will first check with A and B. A and B. So which is again BC and BD. So here you can see A, B, C are in one set, but D is in separate set. So A and B cannot be in the same set, not in same set. Okay, so not in same set. So we will write A separately and B separately. Now C must be checked. So you have to check with A as well as B, because A and B are in separate. So first we will check with A. So AC, they have BC, BC. So both BC are there in the same equivalence, ABC in the first equivalence. So A and C can be together. So you will have AC together, B separate, then D separate, then E separate. So now, even though you have found second equivalence, we have to check again for the third equivalence. If there is no change in the set, you can stop the process. Otherwise, we have to continue. So again AC, B, D and E. So going for third equivalence, you have only combination is A and C. We will check whether A and C stays in same thing. BC, BC. Okay. So BC, BC. Okay, and in this case, you can see again B is now in one set and C is now in one set. Okay. So you can see in this fashion you have to also look, B is in one set and the second for input C is also in same set. So both are in different sets, but for the same input they are having same transition, hence this set is not distinguished. So this is your final equivalence. Now with this equivalence we will find the transition table. So for 0 and 1 we will see what is the transition. Now what is the state we have is AC, B, D and E. So E is your final state. Now for AC, for 0 it goes to B, you can see in the last table here. Okay, and for 1 it goes to C. Now similarly for B, check where it goes. For a B it is a separate state, so you can write the input similarly. So B goes for D, and similarly D we will have the same row value for B, D and E same way. So same inputs. So for D, for 0 it goes to B, and for 1 it goes to E, then for E it goes to B and it goes to C. So the final minimized diagram is, you have AC, you have B, okay, you have E, you will have D. Okay, so now what I do is, AC is your starting state. For input 0 it goes to B, for input 1 it goes to C. So C is nothing but here again AC. So we will put a self transition here 0 because they belongs to same set. So sorry, this is so this is 1. Okay, and for B it has a self transition to 0, and for 1 it goes to D, and for D you have for 0 for 1, so you put arrow mark here and 0, and for D for 1 it goes to E, so E, and for E of 0 it goes to B, so it is E of 0 it goes to B, and E of 1 it goes to C, so here it is C and A are in same set, so we will write AC here, so it will be 1. So this is your minimized DFA for the given DFA diagram, right? So little bit of confusion you will have. We will see in another example. It has a multiple finite sets. Okay, so first we will write these states here. So I have A, B, C, D, E and F. So for the input 0 and 1 we are going to check. So first we will write all the transitions. Here for A 0 we have A, similarly A, this is E, and this one is E, this one is E, and for F it is going to be same. So similarly here it is C, D, F, F, F. So this is the transition table. Okay, so this is the transition, this is states. Okay, now we will start our 0 equivalence first. So I will write it over here. So 0 equivalence. So first you have to form the sets which are not final states. So here consider this E is also a final state here. Okay, I forgot to mention here. So you will be having A, B, F will be in a separate sets, and similarly you will have C, D, E are in separate sets. So here in this transition table you can see it is D, E is okay, D is okay, and C are final states. So now this is 0 equivalence, so it's your first year set. So now we will calculate equivalence 1 with sets of equation 1. So you are going to find equivalence 1 equation. So you will write like this, so it will be comfortable, equivalence 1. Okay, so first we will take ABF set. So let me check for AB first. So AB, you can see it is BC and it is AD. Check A, B are in same set, yes. C and D are in same set, yes. So you can see here A and B are in same set, and C and D are in same set. So A and B can stay together. So A and B stays together. Now I have to check with the F. So let me have AF. For A it is BC and F is FF. Okay, so F is FF, so it can't be in the same set, so you have to write it in a separate set. So F and F. Similarly you check for CDE also. So first let me check for CD. So CD it is EF and this is also EF. So both C and D stays in the same set. Now you have to check for C and E. So check for C and E. So again it is EF and EF. So no change in the final set. So this is your equivalence to equation. So now to make sure that there is no more further change, we will calculate equivalence 2 with equivalence 1. Okay, so we'll write equivalence 2 here again. So we'll check AB. AB again have the same input. Here A and B are in same set, C and D are in same set, so AB stays together. So F is individual, so no change. Next we'll check CDE. It is again same, there is no change, so you will not have any change in this. So you will have CDE in the same set. Now you can stop your process, that is your third set and second sets are same. So with this we will form the minimized equation. So let me write the transition table first. So I will write it over here. So the sets are AB, F, C, D, E. So it's for 0 and 1. So for 0, A goes to B, so which is again B, which is in the same set A, okay. And for 1, it again goes to C or D, okay. C, D, E are in same set, so you can write C, D, E here. Now F, on F of 0 and 1, it both goes to F itself, so there will be no change, so you can have F here. CDE, now check for CDE. So for 0 it goes to E, again it is CDE only, and for 1 it has to go to F, so you will have F here. Now with this, your minimized diagram is going to be AB, then it goes to CDE for 1, and it is having a self transition for 0. So this is your initial state, okay, and still your CDER is the final state here, okay. Now from the final state, for 0 it goes to self transition, and for 1 it goes to F state, and for F you have a self transition for 0 and 1. 0 or 1. So this is your final diagram. So we will see a next example. So this is your final diagram. So we will see the next example, which is having an unreachable state. So which is the unreachable state? You can see here F does not have any incoming state from this one. So you can remove this state and you can continue your process. So no need to calculate the F. So if you have any unreachable state in your DFA, you just remove it. So now let us see what are the sets we have. So we will have it as A, okay, A, B, C, D, E and G. So we are not going to consider for this. So these are states, and for 0 and 1, what is the input? So now for 0 it is going to be BC, and for B state it is going to be DE, and for C it is ED, and for others everyone are going towards G, okay. And one more thing, G is not having any transition, we will take it as 0, 1 here, so we will have GG is here. So here what are the final states we have? We have B, we have C, and we have G. So we will start our first step calculating equivalence 0. So we will form a set with the non-equivalent sets, so A, D and E, and with the final states as a separate set, so which is going to be B, C and G. So first step is created. Now we are going to calculate what is your equivalence 1 equation is. So we'll start. So first we'll take ADE set. So we'll check with ADE. So AD alone. So AD is going to be BC and D is GG. So you can see B and G stays in same set and C and G stays in same set. So you can have A and D together. Now you have to check for A and E. So AE is going to be BC and it is going to be GG. It's similar to the previous one, so still no change. You will have the same thing. Now we'll check for the final states. So BC. So what is BC? BC is DE and E D. Check whether DE and DE are in same set. Yes, it is in the same set, so we'll have BC together. Next, check B and G. Okay, so we'll have B and G together. So B is going to be DE and G is GG. Now D and G are in separate set, E and G are in separate set, so you can't have G together, so we will form G separately. So this is your second equation. Now we will find the equivalence 2, because there is a change with 0, 1 and 1. So we have to find until there is no change. So we will take the same set ADE now. So I will take AD first. So now it is BC and GG. Now if you see, B and C are in one set, but sorry, B and G are in separate set and C and G are in separate set. So you can't have A and D together. So you will have a separate set, A and D separately. Now you have to check A and E with one set and A and D with one set. So let me check with A and E first. So A and E, it is going to be BC and GG. So they have to be separate. But before giving E separate set, you have to check with D also. So let me check with D also here. So D is going to be GG, GG. So you can see it's identical. So you will have D and E together. So A will be separate. I repeat again, in the set ADE, we have checked A and D. Both A and D are different sets for equivalence 2. Now E has to be checked with A as well as D. If A and D are standing in the same set, then you can check with either A or either D. But they are in different sets, so you have to check with both the sets also. Now we will see for B and C, the final states, whether they can stay in the same set or not. So it is DE and ED. So they are in the same set as per in the equivalence 1 equation. So BC never changes. So you have BC and G will be again separate. So now this is your third equation. Again 2 and 3 are different sets. They are not identical. So we will go for equivalence 3. Let us check. So we will have A separately, no change. So DE, if you see the input, it is having GG. So there will be no change in DE also. BC, again they have DE and ED as an input, so both are staying in same set. So again you will not have no change in BC, and finally you have G. Now you can see equivalence 2 and equivalence 3 is similar. You can stop the process. Now you can write the transition table. So you have a transition table A, DE, BC and G. Okay, sorry. So okay, we'll have it like this. Okay, now for A it goes to B. So B here is in the set BC, so you will have it as BC. For 1 also it's going to C, it is also in the set BC. Now for D it goes to G. G is a separate set, so you will have G. For B it goes to D, so D and E are in same set, so you will write it as DE. And for E also it is same, so you will have DE here. And for G it is no change, it's G and G. Now we will draw the state transition diagram. A, for input A it is going to BC. For input 0 and 1. So here first, before going to this, what are all the final sets we have? There is no change here. B and C is the final state and G is the final state. Okay, so your BC will be a final state. Now from BC, next one is DE. Before going to the, from BC I am going to DE. Okay, so for the input 0, 1. Okay, now this is done. Now for DE it goes to G for 0, 1. Then finally you can see G as a self transition with 0, 1. sorry, it's jumping to the end of the page, so it comes to next page. So this is your final minimization of DFA for the given DFA. If a DFA is consisting of unreachable state, the state must be removed and then you have to do the minimization process. So that's all about minimization. Next we'll see pumping limb now. Thank you. So that's all about minimization of DFA.